Hi everyone. So we're going to start with this session, and this one is Learning Enhanced Credibility Transformer, and it's going to be delivered by Kishan Padiachi, Ronald Richmond, and Kovlin Perumal. And I do see two of the three on stage, so hopefully the other one will join them soon. And then, as usual, we're going to do the Q&A as we usually do at the end of each presentation. Gentlemen, over to you.
Thanks so much for that nice introduction, and also thank you to ASA for kindly allowing us to give this session. I'm very happy to take Q&A during, so if anybody in the audience wants to chat, please just raise your hand and let's make it a bit more interactive. I'm not checking WhatsApp, I just need a timer. Okay, so this is a really interesting session, and I'm happy that I have the opportunity to present. Who's familiar with the idea of in-context learning with large language models? So really what it is, let's say you log into ChatGPT and you want it to perform better than if you just, say, ask it a question. So what you can do is you can give it examples of what was your question, what was the answer, and if you give it enough examples, there's this phenomenon where large language models can start to predict, based on those past examples that you've given it, what the answer on a new query is going to be, and that phenomenon is called in-context learning. So that's what the RCL in the RCL paper is all about, and what we're going to try to do in this talk is show how you can use in-context learning for non-life pricing. And it's been a little bit of a journey. Last year at the Actuarial Convention, we were very privileged to present a paper called the Credibility Transformer. And the Transformer is a model which is really at the heart of large language models, and I guess what we call AI today. This paper, or this presentation that we're giving now, is an extension of the concepts from that talk. So what we're going to do is we're going to do a quick review of the Credibility Transformer, and then we're going to show how can you do in-context learning with this model with really interesting and surprising results. And when we proposed this talk to ASA, I basically said this is one of the strangest results I've ever seen. It really is strange that this works so well. And who knows, it might even be useful for pricing your motor book at some point in time. So let's see. So the question we're trying to answer is, can we enhance, sure, this podium's in a bad space. Can we enhance actuarial models by adopting RCL? But also, more importantly, can we understand anything about the RCL paradigm by relating it to traditional methods? That's really what we're going to attempt to do. The paper's online, it's on arXiv, and this is joint work with Kishan, with Salvatore Scognamiglio and Mario Wittrich. And you're welcome to download it and look at it and see if it's valuable. So just a brief review of the agenda. We're going to talk about paradigms of prediction. I'm going to hand over Kishan to give that introduction. And there we're going to try to relate the regression paradigm that we're all very familiar with from non-life pricing to different ideas like k-nearest neighbors, and see if we can use that as a basis for the rest of the talk. I'm going to quickly review the credibility transformer. We'll introduce what the point of this in-context learning transformer is. We'll make some theoretical connections, talk about how we actually get this thing to learn, and show some results. We'll then show how you can use this for zero-shot capabilities. And zero-shot is the idea. Let's say you are rating and you see that there's a new electric vehicle brand in your data set. How can you do some sort of transfer learning based on what the model already knows to that unseen level? That's what zero-shot learning is all about, and then we'll give a summary. As I said, please feel free to ask some questions, and let's make it interactive. Over to you, Kish.
Thanks. Hi, everyone. Thanks, Ron. Cool. So, I wanted to ask, just by a show of hands, who's familiar with supervised machine learning? Okay, cool. So just a bit of a quick recap regarding supervised machine learning. You basically have a set of x's or set of independent variables that you want to relate to a dependent variable y. Okay? And the goal of it is to find some form of relationship between your different x variables to relate to that y variable. So the basic plan of it is that we basically look for patterns in which we can map our x to our y variables. Okay? There's two main types. You have regression modeling as well as classification modeling. So classification modeling is trying to, in a sense, determine whether a claim is fraudulent or not. And regression modeling is trying to work out like a relationship that is numeric. So in other words, like your frequency modeling, your severity modeling. Cool. So in this talk, we're going to discuss the data set that we're going to use is the French motor third-party data set, which Ron has used quite a bit in a lot of the research papers that has been written. And basically, this can be viewed as a supervised regression problem where we have a bunch of covariates x's and we're trying to relate it to a y variable. In this case is how many claims did an individual have based on a whole bunch of covariates. There's two types in supervised machine learning. You get two paradigms. One of the paradigms is a covariate-based method. So in other words, you want to learn a function in order to map your x variables to your y response variable. So it's function-based. It's a mathematical relationship. Okay? This is what we're quite used to in a lot of our GLM models because we want to be able, GLM models are considered interpretable because we can understand the relationship between various covariates and the response variable, right? And I believe we use that quite a bit in our non-life pricing, in your credit pricing, and so on. Okay? One of the beauties about GLMs is that you're actually able to regularize your covariates. Regularization basically means we're going to add a penalty to our loss function that we're trying to optimize if certain conditions are not met. A lot of the work Ron has done using ICE nets and so on. I've tried to build some form of interpretability to deep learning models, which are quite difficult to explain and to enforce some form of actuarial reasonability. Another type of prediction model or supervised learning regression model is KNNs. I just wanted to ask by show of hands who's familiar with KNNs. So something that I found quite interesting when working with this is that I thought KNNs was completely a separate paradigm to something like your ordinary least squares regression or your covariate-based methods because they're based on distance, right? So the basic idea behind KNN is that you are trying to find the nearest neighbors in your training data set such that are similar to what you're trying to predict on. So you're trying to find which y in my training data set am I similar to, and basically you will average those targets. So it's, in a sense, it's a measure of distance. So that led me to believe it's quite different to a covariate-based model, which are based on essentially a function, right? Now, there's an interesting concept. I'm not sure if people remember from statistics when busy with ordinary least squares regression, there's something called a hat matrix. So essentially, what the hat matrix is that by solving that equation on top, beta times your x transpose x inverse, we're essentially learning a relationship of betas in a normal linear regression format that basically represents what we'll multiply each of our covariates by. And the idea basically behind the hat matrix is when we're trying to make a prediction, we say y hat, which is what you're trying to predict, is equal to x times your beta vector, right? Now, if we decompose and substitute beta in for the long format with x, we end up with y hat is equal to that function over there, right? Now, the idea is behind the hat matrix, if we treat this portion over here, we set it equal to h, we actually see that we can relate y hat back to the training data set, training data points y. Okay? So in other words, we're basically saying there's a way that we can move from the y that we were building the model on to what we're actually making predictions on. There is a relationship there, right? Next, I'd like to draw a comparison with KNNs, which are distance-based models, but also have the same hat matrix, okay? So the beauty about it is the hat matrix in KNN is basically 1 over k, essentially averaging out your nearest neighbors for your k data points. So for example, if k is 5, when you're actually predicting on your data, you will also have a hat matrix over there, but it's going to be equal to 1 over 5 for all the neighbors that are closest to that data point. Okay? So the whole idea is two paradigms that we thought were different. One was a distance-based sort of algorithm, and another, which is a covariate, actually share some form of similarity. Then I'd like to show this little graph, just illustrating basically comparing ordinary least squares regression, which we should be familiar with from our campus days, with KNNs, right? So the idea is both of them have a hat matrix, and essentially you can think of these points here as sort of being your Y training points which you built your model on, okay? And as we step through it, when we're making a prediction, we can see that when we start on this side with our ordinary least squares regression, we are sort of weighting our training points depending where we are predicting. And then with KNN, we're doing something very similar where we also are weighting our points, but we're giving equal weights to each of the neighbors. So in this case, there's 3 neighbors. So you can see as you're stepping through, you're basically averaging out these 3 neighbors from your training data set. Okay? Now, one thing that's quite interesting about this is that we're giving equal weight to all our neighbors. So 1 over k1, in this case 1 over 3, 1 over 3 throughout. Now, what Ronnie is going to take us through is there a way that we can, instead of only focusing on k, can we focus on all the training data points, but dynamically using attention, choose where we're going to give more sort of weight, instead of equally weighting 1 over k to each. Yeah. Cool.
Can we turn this one on, please, and this one off? Thanks a lot, guys. So exactly as Kishan said, what we're going to try to do is come up with a way of dynamically reweighting your k-means using a transformer. So let me ask the audience's opinion here. Let's say you've got a fully trained supervised model, like our linear regression over there. Do you think there'd be any benefit in using the hat matrix or any of the other things that you can pull out of that model to do something like k-means? Would that add any information to your predictions? Maybe just think about that a little bit, and let's see if anyone would like to venture a guess. So what are we saying? You've trained your GLM, you've got all of your relativities, and now you're going to try to do something with those covariates that you've trained and maybe find what's a cluster of the policies that share that covariate information and average over the responses. Does anyone think that would be meaningfully different or add any value over and above your GLM? Come on, guys, we've got a bunch of good motor pricing actuaries in the room. No guesses. So I would say it'd be completely useless, because all of the information that you should have got when you're training your model or when you're fitting your GLM, everything's already been captured in that blue line over there. And obviously we used to much more high-dimensional covariate spaces with categories and categorical variables, so it doesn't look as neat as this, but it's essentially just fitting a line through it. So my opinion would be, if someone came to me with that proposal, I'd say you're wasting your time. And the very interesting thing that we're going to show is that even if you've got a very well-trained and quite well-performing transformer model, using some of that information that it's learned in the covariates actually allows you to do k-nearest neighbors in a way that enhances predictive accuracy. Whether or not it's useful for anything practical is something we can discuss at the end, but that's the roadmap of where we're going to go. So let's do a quick recap on the credibility transformer. The reason we're building this work on top of the credibility transformer is what we did in this particular work was come up with a way of representing all of your covariate information, all of your rating factors in a very neat vector summary, which then becomes extremely useful for prediction. And as we run through that, keep in mind we're going to use that neat vector summary as the basis for performing in-context learning as we go through. So the credibility transformer was an idea that we had last year, which tries to adapt the transformer model that underlies all of today's AI applications for tabular actuarial data. The idea was to incorporate classical credibility theory directly into the model's architecture and training. And this was published as a paper in the European Actuarial Journal at the beginning of this year. So basically, what we're going to do is just summarize this in 4 or 5 slides, is how do you get from the pricing data sets that we're all familiar with to something that you can consume with a transformer? The first thing that you do is you need to do embeddings. Embeddings is a way of taking each rating factor and coming up with a vector representation of that rating factor. For categorical features, if you think about the normal way that we fit GLMs, we come up with relativities. You can think of that as 1D embedding. In transformer models, you have many high-dimensional embeddings. I think we use something like 64 dimensions, if I'm not mistaken. And then for continuous features, instead of bucketing those like your pricing software classically does, we pass these variables through small independent feed-forward networks to create also a block or a vector that embeds each variable, each rating factor into a much higher dimension. So the first step when you fit a transformer model is you form a matrix of embeddings that looks like that, and that captures in a relatively high-dimensional way all of the information that you might have on a particular policy. How do you get the actual values of these high-dimensional embeddings? That's something you fit or you learn during the training of the model. As I said, guys, I'm running through this quite quickly. Just feel free to shout if anything's not clear. So how can you get this matrix? So you've got all of these different variables with their relativities. How can you get this model to sort of recognize the context in which you have each variable? And let's just think about some examples where this might be important. You can imagine that we all know that young drivers generally have worse own damage relativities than older drivers. And we also know that often male drivers have got, young male drivers often are worse than young female drivers. If I'm being sexist and generalizing too much, just let me know. But that means that when you have an embedding value for a young driver, it should somehow learn from its own context if we're talking about a male policyholder. Or if you're looking at a building value embedding, that value of the embedding should be different if it's in a flood zone or not, to incorporate that information we have about the relative riskiness of what it's found, of where it is. So we need a method which allows the embeddings basically to pay attention to what is the surrounding context in which it's in. How do we do that normally in non-life pricing? If you're using GLM's interactions, quite difficult to get all of your interactions correctly, and there's a lot of judgment involved. What we're going to present, which is the self-attention idea, which is the main or most important part of the transformer model, is an automated way of doing this. So how does this work? The self-attention mechanism works with two main components for each covariate that you've got. You project, and you know what, I'm just going to skip straight to this diagram. This is a little bit complex, but let's walk through it together. Here are your matrix of input embeddings, and what you do for each one of those embeddings is that you project them into a new space. What does it mean to project? You just pass them through a small regression model. And what you're trying to form are three new matrices or three new sets of information. One is your query matrix, which says, what are we looking for? Another one is a key matrix, which says, what do I contain? And the last one is a value matrix, which says, what information do I carry? So think of this as, let's say that first embedding is age, and that second one is gender. It's going to say I'm looking for something that can enhance my understanding or knowledge of age. And it's going to say, well, that's really similar to the information that your gender embedding has. And the final thing that you get out of this will be a new learned embedding that the model works with. So this idea of query, key, and value is feels very strange to an actuarial audience. It's originally based in database theory, but this is the main thing that the transformer model does when you're using ChatGPT, or one of the main things is run a huge amount of these self-attention operators, and you come up with what we call a context-aware representation. And that context-aware representation, after you do the attention calculation, basically says, we have now enhanced each embedding that you've got, or each relativity that you might have in your model, with information that comes from all of the other variables that you fed through this model. The way that this attention operation works is by assigning scores. So this is the actual formula. Don't worry about it too much, but what the actual formula says is, how much attention does it want to pay to each one of the values in your embedding block? And if you see that each row of this adds up to 1, and that's where we're going to start to get an idea that there might be a credibility component or credibility principle involved in these transformers. So how do we actually make predictions? What happens is if you just take sorry, let's find the right place. If you just take this context-aware representation, where you might have 64 dimensions for each one of the variables that you fed into the model, this becomes extremely high-dimensional. So it's very difficult to get that to produce good predictions because you overfit your data significantly. And what that means to say is you might fit your training data really well, but your predictions out of sample in your test set don't look too good. So what we found is something that's extremely useful is you come up with a pure prediction token. So this is an idea that we took from a paper called BERT. I think BERT stands for bidirectional embeddings of text. What does the R stand for, Kish? Do you remember? Does anyone remember what the R in BERT stands for? Okay, BERT was a big famous model from Google, and they came up with this idea of adding in what's called a CLS, or a classification token. And the idea is that this is a token where through attention it interacts with all of the other variables and all of the other information that you're feeding into the model. You strip this CLS token out at the end and you make predictions with it. And this is an extremely effective way of summarizing all of this information that you've got into a low-dimensional vector summary, and it leads to very good predictions on par, more or less, with gradient boosting machines in my experience. So the question is, how do you calibrate this thing? And that was the main idea of the credibility transformer that we came up with. If you just leave this at its random initialization like you normally have in transformer models, it works, but our insight is that potentially you can force this to produce the portfolio mean or your base rate. So let's say you've got a non-life pricing problem and you want to fit a frequency model. Ideally, what you'd want to do is make sure that you calibrate this at something that will produce your base rate as you go through the transformer architecture. Why would you want to do that? There's one reason, which is after you've forced that to be your base rate, if you think about what the attention operation is going to do, it will give some attention to itself. So in other words, that's attention to the portfolio mean. And the rest of the attention is going to be on the covariates. And you can think of that as another credibility equation. How's it credibility? You've got alpha times by your portfolio mean in the latent space of the transformer, and you have 1 minus alpha multiplied by all the contributions of the covariates. And that just turns out to be credibility between your portfolio average and the individual information that you've got for a particular observation. So that's how do we do that is what we're going to quickly show you on the next slide. If this is too complex, just ignore it. But the basic idea is that you trace a different path. You always allow the model to either pick between what the full model has learned, updating that CLS token with all of your covariate information, or you just take the prior token before any training. And with a certain probability, you make predictions with the token without any information. So another question for the pricing actuaries in the room, what's the optimal prediction to make in a pricing problem if you don't have any covariate information? The mean. Exactly. So if you don't add covariate information, you force that prior token to produce the mean. If you do have covariate information, then obviously you're going to get a much better answer, and you basically force the model by selecting probabilistically between the prior token and the fully developed token. So on the times when it selects to make predictions using the prior token, it forces it to the mean. All the other times it incorporates all of the covariate information, and that's how you make sure that you calibrate this to the mean and you have your credibility operation. This is just a little bit around how it works. At the end of the day, your prediction from your transformer lands up being credibility, a credibility factor times by your prior, and 1 minus a credibility factor times by all of the information you get from the covariates. So hopefully this makes transformer models, which at first glance seem very alien and very different from actuarial methods, into something that we can directly relate to from our studies in non-life. Because our life actuary colleagues don't know anything about credibility, probably this explanation is not going to make it any better. Sorry for the life actuaries out there. Okay, so this is going to be the foundation of our RCL model. And what is the primary output? The primary output that we now have from this model is the CLS token, which contains very rich, summarized information about every observation that you have in your portfolio of business. And what we're going to try to prove as a hypothesis is that the CLS token and the embedding space of the CLS token can act as distance in the same way that we've had a distance function by looking at where things are in K nearest neighbors. So that's the connection we're going to make. Seems like a good time just to stop and take any questions if there are any. Let him turn it on. Try again. Oh, there we go.
Okay, how about now? Cool. Right, so good afternoon. I'm a life actuary, so...
Oh, sorry. Actually, some North American actuaries do use credibility theory. I don't know. I've never seen it in South African context.
So I know a little about credibility theories. Now, just excuse my question. It might just sound dumb. I'm trying to put together everything you have said, yeah? Now, the way I see it, you're saying that you could use the usual linear model, and you're combining it with the Y itself, like any relationship between Y and other Ys. So you put some credibility on that, and then there's also credibility on Y and X's, and you combine those to get a more precise answer.
So I think it's a really good question. Over here, we're just talking about credibility in the covariate space. So we're saying that there's a source of information in your CLS token, which is calibrated as your portfolio mean. And then there's another source of information in your covariate. And the linear credibility model here in the latent space is going to combine those. You'll see in a little bit, so this is credibility only on your X's in a way. So if you think of linear mixed models or generalized linear mixed models, just to throw out another reference, it's very similar to what's happening, but instead of going over the levels, you're going over the covariates. You'll soon see in the ICL transformer, we're going to use this credibilitized token, and we're going to use that to search over the relevant Ys.
I see. Thank you.
Cool. Any other questions? No, we didn't.
Yeah, I don't know about last year, but just a thought, was it in, so it's not really funny, use positional coding where you don't want to take it out.
I think let's get a microphone over to you just so that the video guys who are recording can capture that audio and that question from you.
Sorry, thanks so much. Yeah, in terms of the positional encoding, so for example, if you want to not use the value from a covariate, it doesn't need to be future because there is no ordering here in the covariate space. But let's say we didn't want to take into account gender, only consider age first, and then capture that intention block or that pattern from age only, and then consider gender after, rather than considering them all in one shot, where there is no ordering amongst those covariates. Just a thought as to whether there was ever a consideration for the credibility transformer.
So, sorry, what was your actual question?
Yeah, in terms of not using the positional encoding and leaving that out, because the normal transformer would mask everything that happens in future and only use a covariate or the token from the past to infer that attention pattern. Here, that doesn't use that. Was there any thought to use that positional encoding in the transformer?
So this is a really nice question, and I'll just put it in my own terms. What we do in order to get this transformer to work is you need something called positional encoding. And that positional encoding basically says this is variable 1, this is variable 2, it could be age and gender, like we had in the question in the audience. And the way I understand the question is just get rid of all of these positional encodings and go through these in the correct order. So I think you might be combining ideas from encoding transformers with decoding transformers. And I don't want to go into it in too much detail, but decoding transformers, there is a clear order, which is the order of the tokens. Even there, if you want attention to work properly, you generally need positional encoding. The problem here in tabular data, the reason I think it's very difficult to use a decoding transformer is there is no natural order. So either you need to impose that without reference to what's being learned, or you need to come up with a different solution. And maybe we should take that one offline, because there are some nice solutions, but I'm not sure for tabular data if it adds value. I don't know if that helps.
Perfect, yeah, it does. Thanks, Ron.
Cool, thank you. Okay, so now let's talk about RCL. Let's use everything that we've done and try to work out how we're going to do in-context learning or something like k-nearest neighbors for actuarial work. So we often know that in actuarial modeling, a lot of what people would call the actuarial modeling that we do is something where there's severe imbalance. When you're doing pricing, you've probably got a claims frequency of maybe 15 or 20%. The vast majority of your records don't have claims information. So it's very difficult as a result of that limited data and the rare events to build models with very strong signal. If you've got very strong signal in your models, it probably means your underwriters aren't doing their job. If they are doing their job, then you're not going to have very frequent claim events, at least in non-life insurance. Maybe in health insurance, it might be a bit different. So what's the traditional solution? Like we said, it's often or it was credibility theory, where you have a linear combination of your individual experience and your collective experience. It's in practice very difficult to apply credibility theory because you've got very complex nonlinear patterns, you've got very high dimensional feature spaces, and the assumption that you have a collective that is somehow relevant to your whole portfolio often feels like it breaks down. We know in rating that you want to give very little weight to your collective experience, and what we actually find with the credibility transformer, once you fit it, is that 90% of the weight goes to the covariates, which is exactly what you'd expect. So what we're going to try to do now is work out, can we take our credibility transformer, take that CLS token, and use that to create context among the different portfolios that you have in your book to perform a credibility transformation over those observations. That's really the whole idea that we want to promote or discuss over here, is really using the CLS token, which we've been discussing, to create dynamic context from similar instances that you might have in your data. So let's talk about in-context learning. How can you do RCL in an actuarial context? Your context is going to be similar policies to the one that you've got. And the way that we're going to build that up, you'll see, is in fact using k-nearest neighbors. You're then going to adapt the weights of your KNN using a transformer and using credibility. And through doing this, you can handle new risk profiles, you can handle all sorts of interesting things that classical supervised learning doesn't allow you to do. And a couple of the questions that we'd like to work through in the next section is, can taking a pre-trained model and doing RCL improve its performance? As we said at the outset, the intuitive answer to that should actually be no, in my view. If it's the case, how can you explain it? And the explanation is going to be credibility. And then finally, can you improve your performance significantly using RCL? And the sneak peek ahead is, I think that the answer is going to be yes. So let's look at what the architecture of an RCL transformer can look like. This is pretty much the same setup that we've always had. Let's say you've got your target batch, that's where you want to make predictions, and you're going to run it through a pre-trained credibility transformer model, which is going to give you this magic CLS token that summarizes all of the information in your data set. And what we're going to do is we're going to also take another batch of information where you've also calculated the CLS token, but where you've already observed responses for that group. So think about in your pricing file, you've got a bunch of observations where you've already seen the claims come through. And we're going to take those claims and create something that we're going to add on top of the CLS token. So in other words, for each one of these variables where there is historical information, you're going to take your CLS token, you're going to add a vector representation of the claims together, and that's going to give you what we call a decorated token. Why are we calling it? Think of a Python decorator. Who's used Python and knows what a decorator is? Basically, the way it works is you write a function and then you can decorate it, and that gives that function extra capabilities. In exactly the same way, we're going to take our responses, decorate the CLS token, and then perform a credibility calculation using attention between these tokens which now carry claim information and the ones where you want to make predictions. And what that's going to allow you to do is incorporate some aspect of the claims data into your modeling directly in a way that we don't normally do in anything actuarial I've ever seen in the non-life rating space. So let's talk through 4 of the components over here. The first thing that we want to do is we want to retrieve or pull out records in your data set that are relatively similar to the record you're trying to make predictions for. And the way that we're going to do that, the base token that we're going to use is going to be just your CLS token coming out of your credibility transformer. We're going to mathematically measure how similar that is to all of the different records. And for example, we might pull out 64 records from our data set where there's a baseline level of similarity. So that's the first part. The second part is we're going to, exactly as we've said, we're going to take our claims information, push it through a small neural network, and add that onto what you have from your original transformer. So think of this as your covariate information, and you're going to add the claims information for those records where you've already observed claims outcomes onto that covariate information. Obviously, this is now happening in a sort of a, in the latent space of the model. It's not your actual claims information. So this is the decoration that we're talking about. And there's a little bit of a credibility weight over here where if you've got very low exposure, you try to downweight things. So if you had a policy on your books for a day and then they lapse, it doesn't give you as much information as if a policy is on your book for the whole year. And that's what the point of this term in this equation is. The third part of this is we're now going to use self-attention. So exactly that same operation that we had before in the transformer, where you try to see how important is each part of your information. What we're going to do is we're going to take a self-attention operation between each record that you're trying to make predictions for and each one of these decorated tokens to pick only the most important information up out of that historical information set. And that's going to be learned with another transformer. So that's the point of the self-attention. And basically, we're going to take the same thing that creates your actual predictions in terms of frequency. So at the end of all of these high-dimensional models, you need to make a frequency prediction or you need to make a severity prediction. How do you do that? Generally, you just do it using linear regression. Sorry for the very terse mathematical notation, but we're going to use just a linear regression to make our predictions. And strangely enough, this is actually going to work. So here's another very nice plot that Kishan made. Imagine that we have pulled out 10 or 12 policies over here, and we've got our target policy, and we would like to switch between as we go from a senior driver to a young urban driver to a middle-aged rural driver. What we're going to do using this in-context learning attention is find which are the pieces of information that are most relevant to aggregate together. So hopefully this visual representation gives you a little bit of a feeling for how the in-context learning is going to work. We're going to pull out a batch of information, and then within that batch, we're going to say what is most relevant. And instead of having these sort of fixed weights that you have in k-nearest neighbors, you're rather going to have these dynamically adjusted weights where the adjustment comes from your self-attention operation. So let's stop there, another natural place to stop. See if there's any questions. Alberto.
Thanks. This is more from a, I suppose, practical perspective when this thing gets in a deployment environment. I suppose you need a context batch. Is that the whole training data? Is that a subset of the data, or maybe it's a completely different portfolio that's similar to it? And I'm assuming that batch would need to be stored in some vector database, and it will be part of the prediction sort of process where here comes, a policy with whatever information. You calculate your CLS tokens. You use that to, I suppose, to retrieve the...
It's very similar to RAG, retrieval augmented.
Yeah, okay, so that was my
It's very
question.
similar to RAG. So exactly like Alberto's saying. Sorry, finish your question.
Yeah, well, so it's about maybe the selection of that data and the appropriateness of using it in terms of setting up your vector database. Is that a robust way? does that need to be updated on a frequent basis? Like how, it's like a separate thing to maintain, right?
I would think of it as another degree of freedom in your rating process. Let's say you've got a lot of historical information, but you start seeing a big severity trend, like we did during or straight after COVID, right? And now you're sitting a year in and you want to know what to use. I take the last year's policies because it contains all of the information there about the likely patterns you're going to see. So you probably want to build up something where you can select your in-context batch based on the most recent or most up-to-date experience. I think it's just interesting that it gives you another way of dealing with shifts over time if you're collecting if you're collecting enough information. If you're not collecting enough information and it's a sparse portfolio, then on the other hand, maybe you don't trust your GLM so much, so you just want to use everything that you've got. So I just think of it as something you can control. Obviously, practically speaking, someone's going to say, hey, latency is going to be a problem. People are going to drop off your website by the time you do RAG, select your batch. Okay, fine. Someone will work out how to make it work. Okay, yes. Alberto, are you happy?
So to overcome that problem, would it make sense to maybe select a small subset of points across the feature space that are representative of recent claims experience?
Model points. We're back to model points.
Yeah.
There you go. That could work. Any other questions?
Sorry, maybe it's a bit trivial, but how is the neural network selected that transforms the claims data?
Really good question. We actually just did something very simple. I think we just had a simple 2-layer feed-forward network. It worked really well. Because all you need is a simple vector representation of what each claim is going to be. To caveat what I just said, we did it on frequency where you don't have a huge range of outcomes, so it's very easy to learn 5 or 6 representations. Maybe on severity data, you need to do something a bit more interesting. Cool. So why should this work? I mean, what is the point of, what are we gaining by doing this? So think about attention as another generalized credibility formula. So in my SAM talk, I said it's square root of sum of squares all the way down. Here, I'm going to say that in this model, it's credibility all the way down. So if you think about your normal credibility in the Bullman-Straub setup, you've got your individual, you've got your collective, and it's just alpha times by one and y minus alpha times by the other. Think of attention-based credibility as a dynamic credibility calculation. So what you're going to do, you've got your CLS token, which you're going to give some credibility. You've got all of your decorated tokens over there, and you're going to just work out how much credibility do you give each one. And your final answer is going to be a credibility weight between your basic information that you have for each record and the augmented information set that you can pull out from all of your other records. So it's basically the answer is the reason why ICL works, at least in an actuarial context, is you're performing a credibility weighted calculation between the information you have about each record and the information that you have with all of your other records. So hopefully that makes it seem a little bit less foreign. And in the paper that we discussed earlier, there's actually a very nice statement of a proposition that in ICL, each causal attention head performs a credibility calculation. And yeah, more or less the proof falls out exactly when you look at the fact that your credibility weights sum up to 1. So it's actually not all that complicated. I'm not going to go into the math too much. Something very interesting that Mario Wuttrich pointed out to us is generally if you want to stay in your covariate space in X, what you're going to do over here is we're going to be using your decorated tokens. And those decorated tokens contain claim information. So it's also possible to do this, and this is a little bit more theoretical, so I won't go into too much detail, focusing only on your covariate information and not performing attention using your outcomes. And then this is a little bit better from a purely theoretical perspective. Let's talk about the learning procedure and some results. So we do this in 3 phases. Phase 1, we train our basic credibility transformer. We if you want to understand the details there, you can look at our paper from last year, performs relatively well. The second stage is we are going to do some fine-tuning only on the in-context learning. So we're going to insert the decorator, which is going to pull out the claims information, and we're going to introduce 2 more transformer layers, and we train this using these settings. Also, I'm not going to go into in too much detail, but this makes a lot of sense for transformer training. And then finally, we train the whole model for a little bit. So you see there's phase 1, phase 2, and phase 3 in the training. How do we get this? So we are going to pull out some information using k-nearest neighbors to form our context batch. I think we pull out 64 rows per observation. It takes a little bit of a while to do that, so latency would be a problem if you wanted to do this practically. And here are some results. So the model that we trained had a Poisson deviance of 23.74. Adding in context learning improves that to 23.72. So not a huge jump, but a little bit of a jump. Fine-tuning it improves it to 23.71. And then taking 5 runs of in-context learning on top of a credibility transformer gets you to 23.67. So that's 0.08 difference from where we started, and that actually is highly significant. I mean, moving to a poorly tuned GBM from a GLM on some data sets won't even give you 0.08, just to put it in context, if you'll excuse the pun. So the basic question that we asked is, can you take a supervised learning model and enhance it using in-context learning? The very strange answer to that question is, yeah, it works. And for me, that's one of the most interesting things I've seen in my time working with deep neural networks. So let's look a little bit at what happens. And I'm going to skip a little bit ahead to principal component analysis of 1 or 2 claims. And let's start with this one, where your credibility transformer predicted a frequency of 0.02. You then push it through the various different layers of the network, and you land up with a much higher prediction of 0.085. What is the space that we're looking at things in? This space is principal component analysis. So what we've done is we've taken the CLS tokens, which might be 64 or 128 dimensions, and you condense those down to the smallest linear space of 2 dimensions that gives you the maximum information, and you get something like this. So what happened over here? This was clearly a bad prediction that you got from your model. And it's a very interesting thing when you fit machine learning models for pricing. Sometimes you do get crazy predictions because there's a new policy that's coming in that you may, for example, have never seen before and never trained the model on. In this case, you got a pretty bad prediction, and in the end, it moves it around the space until you land up with something much more reasonable. I think that's the most extreme one that we saw from here. In this second example, it goes from 0.04 to 0.046. So you can see that really what it's doing is it's condensing some of these predictions down. Let's look at some of this other PCA information. So this is these diamonds. Sorry, this is a little bit difficult to see, and we're going to try fix it up. The triangles are your final predictions. So everything kind of gets pulled into a slightly more central space in the first stage of training, and in the second stage of training, again, it all lies on some line. And really what the point of this attempt to do interpretability here is to show it's not like you had a whole bunch of observations scattered all around and they move to a different place. You stay relatively in context by performing these operations. So why would you want to do this besides for improving the performance and the capabilities of your pre-trained models? One might be, let's say you are pricing, and we all know we hate those big high cardinality covariates like brand or region or something where all of a sudden something new pops up. How do you solve that problem? You can set it to the mean, you can apply judgment. What we're going to show over here is that you can do zero-shot learning. And the way that that's going to work is we're going to just learn from the most similar tokens that you have in a particular data set to the ones that you've never seen before. So what is the goal in this zero-shot analysis is saying, can we generalize using RCL to unseen regions? What we did is we took the smallest regions in this data set, totaling 10% of the exposure, and we just remapped these to unseen. So this is exactly what you'd see in your pricing data set. Suddenly you've got BYD popping up in your car brands. It's a new level that you've never had before. And to help train this, so that's going to be our test set. Our training set is, we took, I think, another 10 or 15% of our regions and also mapped them to unseen. And what we're going to do is we're going to have context only from your training distribution and see if we can outperform a model where we train on these unseen levels. So this is our zero-shot setup. We've got 76,000 observations in our test set, 600,000 in our training set. You can see the frequency is a little bit different. So not only is it unseen levels that the model's never seen before, this actually has a relatively significant impact on the base rate for that unseen portfolio. And will our model succeed in doing something useful in this context? So these are just a couple of results. Your null model, if you just predict, I think this was the mean, hey Kish? The average frequency of your training set gives you 21.091. The basic credibility transformer gets you to 20.28, and that's training with an unseen level. So in your training data, you've got an unseen level. In your testing data, you've got another unseen level, but it's not the same level because of how we set this up. So it does better than your baseline, as you'd expect. And now, interestingly, very interestingly, when you start doing RCL, you start improving over and above your basic supervised learning. So what is the point over here? The point over here is that this can be a really useful mechanism for zero-shot learning. If you get a new brand or a new postcode or something else you've never seen, this can actually help you come up with a more credible prediction than just having an unseen category. Of course, you could say, maybe we'll do imputation or something else, but here's another option for your toolkit. So let's summarize what we've seen. Basically, we've tried to go from the world of foundation models and GPT series transformers, where they discovered this idea of in-context learning. And what we've tried to do throughout this talk is say, how can we take this idea of in-context learning where you give your big pre-trained models some idea of examples and outcomes? How can we take that idea and apply it in a non-life rating context, very different from entering things in a chat interface on ChatGPT or Claude or your favorite LLM? Can we do this and take these ideas and transfer it to an actuarial context? And hopefully by now, at the end of this talk, you'll agree that the answer is yes. And if you want to see a few references where this is happening wide of this, Tab RCL is a really nice implementation by a fellow called David Holtzmuller and some other European co-authors, where they do this at scale for tabular machine learning. The major difference between what they do, if you look at that reference, and what we do is they train on a huge bunch of data. We're only training on one data set and showing this is feasible in what should be very similar to our actuarial context. And with that, I think that's it, and let's take any questions.
Thanks, Ron and Kovlin, for quite a great presentation and discussion. Are there any questions?
Hi, Ron. Great presentation, thanks. So I guess summarizing in my own words, you haven't built a pricing model, but now you've built a pricing agent.
You could maybe think of it like that. Yeah.
It's tongue-in-cheek, but I guess my question is, there's, I guess, a relatively quite a young audience here with a lot of people interested in this stuff, but how do we get the decision makers at insurance companies and the senior sort of actuarial teams to buy into this modeling techniques?
Will make more money.
I guess, yeah, okay, cool. That's the question.
Less tongue-in-cheek than that is, I think this is very experimental. So this is maybe pushing it quite far. I think a lot of stakeholders in non-life rating are now comfortable with machine learning. Slowly, there's starting to be a bit more acceptance in life and in health. I think if you wanted to do something like this, it's always good for senior actuarial stakeholders to bring it back to the basics, which is what we're trying to do. If you went to a bunch of stakeholders and said we did RAG over our policy data sets and the results look better, I don't know how much credibility you'll have. I think if you connect it back to classical ideas of K nearest neighbors or credibility theory, if it's an actuarial stakeholder, I think you might have a little bit of a better chance. Of course, I'm not recommending that you do this in practice. This probably needs a lot more experimentation, and some of the risks that we haven't even spoken about, like Alberto mentioned, are maybe context shift. Let's say things are rapidly changing and your historical data is no longer relevant. There's also, I mean, it's just a new paradigm, and I think it needs, just like 10 or 15 years ago, GPMs were a new paradigm, and it's taken us a long time to get on board. Maybe because we followed that journey so many times, it can be a quicker journey, but it still needs a journey for something like this.
Okay, thanks. I guess the AI stuff is a bit of a bubble as well, so maybe we can write that, you know.
Yeah, thanks for the question.
Thanks. Any other? There's a question this side, at the front. No, second row, rather.
Thanks, me again. Thanks, Ron, Kishan. Yeah, I think this is an excellent extension to your paper from last year. My question relates to the K nearest neighbors for the decorated tokens. So now you mentioned the latency issue, which is important for real-time application of this model. But putting that aside, did you guys test the different choices for K? So I know you use 64, but how does it scale as you use, figures lesser than 64 or greater than 64? Do you see, improved performance of the model?
Yeah, it was quite interesting. I mean, we just landed on 64 and it worked. You could extensively hyperparameter sweep here. Maybe important to say is we choose 64 observations for each, but then we combine that into a final context size of, I think, 1,000, by just taking the most hits that we get per observation. I think there's a lot of room to make this better. This is just a quick back of the envelope hyperparameter choice.
Perfect, thanks.
Cool, thanks very much, Ron. Question from my side. So obviously the results are very good, and I think part of that is probably just because it deals with interactions in a better way. It can kind of spot those a lot more. Is this something that can be used to inform your GLM modeling? So can you look under the hood and see there's these interactions that we should be taking into account and then use that in your GLM?
I think what's really interesting is if you wanted to this is a big, heavy model, and particularly if you take that the explanation at the end is credibility, it might be hard to tease out exactly what the boost is coming from. I would say make predictions with a big, heavy model like this, but then instead of predicting on claims information, try to predict the output of this model with your GLM, which is model distillation. And probably you'll pick up there much more easily in a regularized way because of the credibility. You'll be able to pick out which factors are important, what interactions are important. So I think you could, John, but I'd probably do it that way.
Cool, thanks.
Thanks. There's two questions at the front. We'll start with the lady.
Thanks, Ron. For that latency problem, how would you deal with it? I'm just wondering, and I know we always do pricing work with our old data, etc., but with credibility, is the only way we could allocate, some sort of credibility to new information, model points. Yeah, I mean, it's dangerous maybe to start coming up with like, where do you think it's gonna go? Or maybe at least use recent information even though it's not built in your model that you spent months on. So just any thoughts around how to deal with the latency issue?
So I think one is that you've got highly efficient vector databases now. So we just did all of this in pure Python. We didn't use anything over and above that. For people doing RAG, like we've been mentioning, which is where you put something into a large language model and it searches over a store of all of your documents to see what's the most interesting and important context to pull out. If you took one of those vector databases like Pinecone or some of those other implementations, that would probably speed it up dramatically. The other one is you could see what are just the most important observations you keep coming back to, and particularly if things are training, just update your model on those. Because the model's telling you this is where the important information is. Once it's focused on that, just do a little update there. Cool.
Oh, thanks. Thanks for the great presentation. I think it shows great creativity and technical competences also. Thanks a lot.
I'll take that. My job is done. Goodbye.
Now, I was just curious. I might have missed it, but in terms of the training process, when you update your parameters, can you touch a bit more about the algorithm that you use there? Is it like a gradient-based
It's
kind of
100%
algorithm?
gradient-based. So if we just go back to this slide, oops, all gone. You just set it up as a model in Keras or PyTorch, and you just use stochastic gradient descent. We used the Adam W optimizer, which is sort of the industry standard for transformers. It's all implemented, doesn't take much, but it's all gradient-based.
Awesome, thank you.
Cool.
Any more questions? I must say, being an... you've got... Okay, there's a question at the front. Oh, it wasn't a question. Thanks, Ron. I must say, being an investment actuary, I did enjoy this, but I was glad there was a lot of questions because we've been told to ask questions if there's no questions.
Thank you very much.
Just some announcements from my side. Firstly, thank you so much, Kishan and Ronald, for that presentation. But in terms of the announcement from my side, if you haven't picked up your wristband as yet and you want to join us for the Courtside Center cocktails, you still have time to be able to pick that up outside the Exhibition 1 entrance. There's a team standing by to hand you those. And then also, yesterday, you would have seen that Actuaries Without Frontiers video where we are basically collecting 400 Rand to feed a child. So far, we've raised just over 215,000 Rand. So yes, that's really good. So if your organization wants to sort of pledge directly, the ASSA team is standing by. They will be able to invoice your company for ease of payment. Or alternatively, you can still do it using the QR code at the back of the program or the various QR codes around the venue. And I think I've touched on all the important things. Have I forgotten anything?
No, the last session is the plenary.
Yes. And that's in the main room after the break, which we are going into just now. And we'll see you back in the main plenary room at just after 4, so 16:05 sharp. That's it.
Thanks.